Hi everyone. Today we're going to be talking a little bit about concentration and molarity. And concentration and molarity is really important for us because it really tells us, especially in chemistry, like for instance, I have this beaker here, right? And if I tell you that that is 12 molar hydrochloric acid, for example, what does that mean, right? So, is that dangerous? Do we need to worry about that? Up until this point, you've basically just kind of taken what the teacher tells you, right? And the 12 molar, you just hear that, and you don't really know what that means. So today we're gonna dive into what that 12 molar or what molarity actually is. So there's a couple of different ways that we describe this idea of concentration. So really, it's a good idea to start off with a quick definition: the amount of a particular substance in a given quantity of solution. So basically, how much of something is in that solution, right, that we made. So there's a number of different ways that we measure concentration. The four that we're going to focus on today, we've highlighted here. So we're going to talk molarity. That's the main one that we use in chemistry. We're going to talk mass or weight percent. We've already actually talked about that one, but I'll kind of refresh your memory on how to do that. And then two that are really important if you go into the field of maybe environmental studies, looking at pollutants. We use parts per million or parts per billion in order to determine these really, really small amounts or really small concentrations that might have a really, really large effect. So the first way we'll look at determining concentration, we've actually already kind of visited when we did the soda lab way back in the first semester. So with the soda lab, we were actually looking for density, but we had you basically create these different sugar solutions that were different percentages. So let's just revisit how to do that. So if I want to make a 20% sugar solution, right, and I want to make 250 grams worth of that solution, how would I go about doing that? Well, the first thing that we need to be aware of is that the 20% sugar solution, remember that that is basically, we took 20 grams of sugar and that is 20 grams out of the 100 grams of solution. All right. And now I want to make 250 grams of solution. How much sugar would I need to add to that, right? That's my X, what I'm trying to find. So you'll probably notice the way that I set this up, now I have this proportion, right? And hopefully we know how to solve this by now. We're going to cross, multiply, and divide. So I'm going to take 100 grams, and I'm going to multiply that by X, and that's going to be equal to, I'm going to take 250 times 20, and when I punch that in the calculator, I get 5,000 grams. So I cross-multiplied, now it's time to divide. I want to get that X all by itself, so I'm going to divide both sides by that 100 grams. My X is going to equal 50 grams. All right, and the unit on that would be sugar. So I'm going to take 50 grams of sugar, and I'd fill it up. If you can kind of picture this, I'd put 50 grams of sugar into the beaker, and I'd fill it up with water to make that solution. So another way that we calculate concentration is this term parts per. And you notice we don't have anything here because it could be parts per 100, it could be parts per 1,000, but a lot of times we use parts per when we're talking about really, really small amounts, like, for example, pollutants. Our example here deals with the pollutant lead sulfate. If we get that lead sulfate into, say, a lake, how many parts per million would that actually be? So in this kind of picture, this is something that we usually kind of pass around. This is a bottle that has 1 million beads in it. This has 1 million beads in it. And in this example, one of those beads is actually dyed red. right? Just to give you a little perspective on how small of an amount we might be talking about. But again, those small amounts can have really, really large effects. So if we were going to solve a problem like this, even though there's nothing on your homework, but I thought it'd be important just to talk really quick about, if I have 0.045 grams of that PbSO4 out of, again, 100 gram of solution, again, we want to set up a proportion here out of 1,000,000 grams of solution, where what we're trying to find, this parts per, is going to be our x. So again, same process where we would take 100 times x, set that equal to 1,000,000 times 0.425, and we get 425,000. And again, that's grams. And we're just going to, again, divide by 100 on both sides, get that x by itself. And what we find is that our x equals 4,250 grams of that PbSO4. And the way we would actually label this is that we would actually call it 4,250 ppm. That stands for parts per million. And if we were talking billions, obviously we change that m to a b. So the last, probably the most important concentration, at least for chemistry purposes, is concentration in molarity. All right, and we calculate molarity by, which is its own kind of unit here, is we signify it with a capital M, and it's actually moles of our solute. If you don't know what solute means, again, go back and kind of watch those videos on some of the vocab, but the solute is what gets dissolved, and then that's over liters of solution. All right, so that's kind of the total end result. Now notice one key thing that a lot of students screw up here is that this is in liters, right? So if the problem gives us milliliters, we got to change that. So down here you'll see something that might be helpful to maybe put in your notes here about how to change grams. Remember, we should be able to go grams to moles by looking on the periodic table. And then also, if we need to go from milliliters to liters, we take milliliters, we divide by 1,000, and that'll give us liters. So let's actually try this out and actually solve a problem, a sample problem that you'll see on your homework. So it says, what is the molarity of an HCl solution? And it gives us a volume of 450 milliliters and 78 grams of HCl. So we've got some steps here. If you're a steps person, feel free to jot these down and use them. Our first step is to convert the mass of HCl to moles. So I'm going to take 78 grams of HCl. I'm going to set up a little T-chart, or if your teacher uses parentheses, you might do that. And I look up on my periodic table, and I see that 1 mole of HCl weighs 36.5 grams. All right. And when I do that math, punch that into the calculator, 78 grams divided by 36.5 grams, I find 2.14 moles of the HCl. Next, we go to step 2. We're going to convert milliliters to liters. So in this instance, the problem is giving us a volume that is in milliliters. So if it's in milliliters here, we've got to change that into liters. You might have to do this step, you might not. Same thing with the grams. If the problem gives us moles, we could skip this step. But we know that 1 liter is 1,000 milliliters. So I end up with 0.45 liters. So my last step then is to actually plug this into the equation. Now the equation, remember, molarity is a capital M, moles over liters. So when I plug in these numbers here, I'm going to take 2.14 moles and I'm going to divide it by 0.45 liters. And that's going to give me an answer when I do that math of 4.75. And the unit, remember we always want to have a unit on our answers, is a capital M, which stands for molarity. Let's try one more before you go and try it on your own here. It says, what mass of KBr is present in, we've got 25 milliliters and 0.85 molar solution of KBr. So step one was to change from grams to moles. Well, we're trying to find, in this case, we're trying to find a mass, right? Remember, mass is grams. So that's actually what we're going to be solving for in this problem. So we're going to skip that. We do still need to change milliliters to liters. So let's go ahead and let's do that. We're going to take 25 milliliters and we're going to convert that. 1 liter is 1,000 milliliters. And when we plug that in, we see that that is 0.025 liters. Okay, so now at this point, using the molarity equation, let me just write that out again, moles divided by liters. How do we solve? Because if we find moles here, then we can change that into grams, right? But how do I solve for moles? Well, in this case, it really kind of depends on your math skills. So if you're able to rearrange this, you probably notice that we're going to multiply both sides by liters to get the moles all by itself. If that math is, if your algebra is not as strong, make sure you have these three equations written down. So our moles is going to be equal to our molarity times liters. And if I further rearrange that equation to solve for liters, right, L is our moles divided by molarity. All right, so those are really the three, I guess, equations that you should have in your notes if, again, like I said, your algebra is not so great. So now let's plug this in. We're going to find moles by taking molarity, which the problem tells us is 0.85 molar, times the liters, which we just found, 0.025 liters. Do the math, and that comes out to 0.021 moles KBr. So you might think, oh, yes, I'm done. I did all the work. That took so... Wait a minute, not so fast. This is asking for grams. It's asking for a mass. One last step. Don't stop before the finish line here. 1 mole of KBr. We look on the periodic table and we see that if I add a potassium, add a bromine, I get 119 grams of KBr. So now I'm going to take 0.021 times, multiply the top, divide by the bottom, times 119 divided by 1, and I get 2.5 grams of KBr, which would be our final answer. So if you have any extra questions, make sure that you talk to your teacher, but hopefully this was helpful in understanding concentration and molarity.